So just to start with, I just like to put a plug in for Dave's presentation. He was the one that talked to you about operations and process control stuff. I think it's really critical for you as pretreatment people to be able to talk to operations and be able to kind of speak the same language. You guys have totally different acronyms and all that stuff. But when there's a problem, you're going to need to talk. You're going to be able to need to communicate, and you need to kind of develop that relationship beforehand and kind of understand what each other do to help you as you try to work through a problem. I'd also like to put a plug in for the lab. The lab's the same way. The three groups that are going to be involved when you have a situation with wet testing, a wet testing failure, is going to be operations, pretreatment, and the lab. So my presentation is going to give you the basics, kind of some of the words, and so you kind of understand what's happening with wet testing, so that when it happens, you can contribute to the discussion, okay? I guess that's kind of the main goal of what's happening. First, what we're going to do is we're going to introduce the organisms. We're going to go through some of the terminology that we have. We'll give you a quick summary of the different tests, acute and chronic tests. We'll talk to you about some basic statistical stuff, but don't freak out. It's okay. You'll be able to understand, I think. We'll talk a little bit about what happens when you fail, and if you continue to fail and have a significant problem, you do a toxicity identification evaluation, and we'll just explain to you the basics of that and give you some examples of some of the TIEs that I've seen or been a part of. So first of all, whole effluent toxicity came about as part of the Clean Water Act. The Clean Water Act was done in '72, and it says there's no discharge of toxic compounds in toxic concentrations. So the only way to know what that is, because there's like hundreds of thousands of chemicals and how do they affect your receiving water and the organisms that are there, the only really way to do it is to put live organisms in it and see how they do. So the EPA developed the procedure to do wet testing, and is just that. We raise organisms in the lab, you send us your water, we put our organisms in it, we monitor survival, growth, reproduction, things like that, and decide if you're okay or not. Okay? The organisms on the top, my left, are Cereodaphnia. The bottom picture is, let's see, the laser is in the middle. So this is a Cereodaphnia. It's a freshwater shrimp. It has an exoskeleton just like the shrimp that you eat at a restaurant. These are the babies. They're growing into it. Cereodaphnia are very unique in that they reproduce, if they're healthy and in a good environment, they'll reproduce by budding, which is like a plant. Okay, the babies are genetically identical to their parent, which is really cool and helps in the lab because they're kind of the same, right? This is kind of give you an idea of the difference between the size of a baby and an adult. When we test, we use the babies. Start with babies. Acute test, they'll be 1 day old. A chronic test, they'll be about 8 hours old. Chronic test, you're just looking at survival. A chronic test, you're going to start with the baby and you're going to end with an adult, and you're going to keep track of how many babies did they have in a week. So it's kind of interesting stuff. This is how we do it right here. Sit and look at a microscope. The babies are about the size of a pepper grain in the water. So you can see them with your naked eye if you know what to look for, but it's just right on the edge of your vision. So we do it through a sorting microscope. So that's the one organism. This is the other organism that's commonly used. This is a fathead minnow. It's a fish that's common in the Midwest. Warm water fish. You can see the rulers there, so you get an idea of how big they are. This is an adult male. Remember, they're called fatheads, so they're named after the males. So then this was a female. Okay, we raise them in aquariums, such as this. If you can see this, sorry for the people in the back because you probably can't. This is a bunch of fish eggs on the inside of a tile. We collect the eggs and we hatch them. That's what's in these flasks. And when we do testing with fish, for acute testing, we use fish that are between 1 and 14 days old. To do chronic testing, we start out with fish that are 1 day old, and then we feed them and grow them for a week, and then kill them, dry them, and weigh them. So to give you an idea, what does that mean? Somewhere along in here, I got another picture. I'll show you the fish. That's not in there. Okay. So terminology. With acute testing, you're just looking at did they live or die. You put our organisms in your water and you just monitor through the test period, did they live or did they die? That's all you're looking at. The main acronym to know is LC50. That's a lethal concentration where 50% of the organisms died. Okay? To pass, you have to have more than 50% of the organisms live in 100% of your effluent. Okay, if more than 50% died, you failed, and then you have to do more testing. In a chronic test, you're looking at, you don't focus on survival, although survival is a part of the test. You focus on, for the Ceridaphnea, it's how many babies did they produce, and with fathead minnows, it's how much did they grow, how much weight did they put on. And you compare that back to the control. So every test has a control, that's laboratory water or your receiving water, one of those two. Whatever the performance of the control is what you use to judge what happens in the dilutions. Okay? Your permit will be based on the IWC, in-stream waste concentration. That's what portion of your effluent is made up in the receiving water. I didn't quite say that exactly right, but if you put in 1 MGD into a river that flows 2 MGD, your IWC is 50%. That makes sense? So what portion of your effluent contributes to the flow of the river at that point? So for every POTW, that number's typically different. I've seen them anywhere from 5 to 100%. We do have clients that have to pass at 100%, which is really super hard to pass. I feel bad for those people that have that. The other acronyms you might see so IC25 is the main acronym you have. It stands for inhibitory concentration, 25% different from the control. So you're just looking at the control grew to be 100 milligrams. If any of the dilution at the IWC, if it's 75% less than that, or 25% less than that, then you would fail. Other acronyms you might see is NOEC, LOEC, no observable effect concentration, lowest observable effect concentration, and MSDP, which is your quality control check on a test. So we kind of talked quickly, acute testing, do they live or die? And then there's some test criteria for how you would set up a test. They're based on 20 organisms, so not that many per dilution, but it's enough to do statistical analysis on. We've talked about this, acute and chronic endpoints. Acute, they live or die. Chronic is a sublethal effect. Okay, didn't kill them, but it is causing some inhibition of growth or reproduction. Okay. So basically, the sum of that is really in that red. The organism is having to put forth energy to deal with your effluent that is robbing or taking away energy that would be put forth for growth or reproduction. So that's what sublethal means. Didn't kill them, but it's causing them to burn up energy in other ways. Oh, here's my pictures of the fish. So in a chronic fathead minnow test, you start out with a 1-day-old fish. Okay, grow it up for 7 days, fed it, babied it, it's going to be about that big. That's about 0.4 milligrams. Okay, so we have really sensitive balances, obviously, to weigh that. And that's what you would typically see. Run 7 days, you feed them every day. Again, you're looking at IC25 statistically different from the control. Ceredaphnia test, kind of the same thing. Take the babies and grow them up for a week. Keep track of how many babies they produce. Healthy Ceredaphnia can produce 15 to 50 babies in a week. So it's pretty amazing. Again, if the Ceredaphnia is experiencing negative effects, they'll produce less babies. They'll be smaller and stuff, but they'll produce less babies. We use software that does point estimates. A test involves a control and 5 dilutions. So 100%, or one of the dilution series is 100%, 50, 25, 12.5, and 6.25. And that's the percent effluent that's in that dilution, right? You see what differences that concentration makes. So the point estimate will go between dilutions and estimate out what that endpoint is. You might also see the acronym TC with a capital T, capital U, a little c, or little a. That stands for toxicity unit. If it's an A, it's acute. If it's a C, it's chronic. That's an acronym that has come about because when you measure toxicity, you're reporting it as a percent concentration, so it's actually the number's getting smaller. So a small number actually means a lot of toxicity. That's kind of backwards for people to think about. So they came up with TUC, which is just 100 divided by the IC25, so it just kind of flips it so more toxic number is bigger. So it is more, kind of fits people's thinking process better. There is hypothesis testing rather than point estimate testing. I don't know of any states in the region that use hypothesis testing, but you're kind of looking for the same numbers. That's where the NOEC and the LOEC come into play. No observable effect and lowest observable effect. Okay, so if you look at your permit, you'll have a section in Utah, it's called Effluent Limitations. And what you're looking for, you'll have boxes that are a row that's your wet testing stuff, and you'll have your criteria of where you need to pass. Okay, so for an acute test, they have to pass 100%. On this particular client, also had to pass chronic at 100%. You'll also have in your permit below this section, you'll have a written description of your wet testing requirements. Make sure that those are the same. They say the same thing. We see that in Utah, very common in the permits where Sarah should probably give me a stink eye about it, but we see a lot of problem with that where the written part will say something different than the table. You just need to work that out in your permitting process. That's a bad thing. So this is what the written part in Utah looks like. Tells you exactly what a chronic toxicity, what's a pass, what's a fail, the quality control stuff that has to be passed. When we do a test, this is kind of what the software produces. When we finish the test, we put all the data into the software program, and it comes out with some tables. And that's just data recorded. Depends on the software program you use, but this is a chronic test. It'll tell you the IC25 right there. It also calculates out different ICs, inhibitory concentrations, but that's the one that's listed in your permit. This is the thing I would really recommend that you look at. This is given with the second page of this particular report because it's a picture of what the data is. It's a lot easier to look at a picture and understand what's happening. Okay, so this is your control right here. And then this is the 5 dilutions. Okay, so it's the dilutions actually did a little bit better than the control, the lower dilutions. Then you get to this point and something happens, and then your growth dropped to there. So that's at 50%, I believe that says, and 100%. This line is what's in the permit. So when you cross the line, you fail. So you can kind of see visually, okay, it's a problem, it's out towards the higher dilutions. And again, this is where we fail. So look for the table if you need to kind of understand or want to understand an easy way to understand the data, let's say it that way. Okay, so the question is, what happens when I fail? Your permit will tell you what you have to do when you fail. And different states or different permit authorities have different schedules of what you do when you fail. But most people are like the guy in the picture crying because it requires you to do additional testing. Wet testing is the only lab test that I know of that if you don't meet your permit requirement, you actually have to do additional testing. And it can be pretty intense. Once you start failing, it's kind of this black hole that's going to suck you down because you have to be able to eventually identify the toxicant and take it out of the solution because you need to pass, right? Because no discharge of no toxic compounds and toxic amounts. So they have what they call accelerated testing. Different permit authorities have a little bit different take on what accelerated testing is. So I'm just telling you what Utah does. You fail one test, you're required to test up to 5 more times. The next 5 weeks you will test. And if you pass 2 in a row or 3 out of the 5, you're okay. And it's just considered a random, something happened, an industrial discharger dumped to you one time and it's done. It's not a reoccurring problem. If you fail 2 in a row or 3 out of the 5, then you have a problem, a reoccurring problem, and you have to solve the problem. Okay, you've got to fix it. Again, your permit will tell you what you have to do. Call your permit writer if you need to for clarification. The new permits in Utah, for those of you who are just getting your permit renewals, have a very similar wording for the chronic tests when you fail. It used to be once in the next 30 days, and then you talk to the state and work out what the plan is. Now it's similar to the acutes, is you have to test 5 times. It's once every 2 weeks for the next, so that's 6 weeks, I guess. Anyway, again, pass 2 in a row or 3 out of 5 and you're okay. Fail 2 in a row or 3 out of 5, you have to go to the next level of testing. When you fail, you have to notify your permit writer immediately. They need to know, and they'll be involved in what happens next. So the first thing that we recommend is a plant review. And if you read that first line, 70% of the failures that I've seen in my career, been doing this for 30 plus years, it's a plant problem. Dave kind of hit on this too, that you can have things happen in the plant that'll actually cause you to fail wet testing. So start there. Because it's easier to fix it if you can fix it fast and know that it's just us. We had this happen. We had a power outage and this piece of equipment didn't come back on. And so our ammonias are, through the roof. If you identify that as the problem, you can submit that to the state and just a corrective action like, okay, in a week, we monitored the plant for a week, and a week later, we're back, everything's good, our ammonia numbers are good, you're fine. It can end right there. So look at the plant first, be very proactive. The thing the state really doesn't like is if you sit around and think about it for a month and then try to fix the problem. They don't like that. So things that it could be, things to look for at your plant is how close is your plant to capacity. Plants that are way under, that have a lot less flow than what they're designed for or are right close to capacity, those are the ones you seem to see a lot of the problems with. Changes in any kind of chemicals. If you use a certain kind of ferric chloride and you change the supplier and all of a sudden you're failing wet testing, that's somewhere I would look. I would track back through that supplier, what kind of contaminants does he have in his ferric chloride, you know. Same liquid chlorine. I've seen liquid chlorine be a problem. Anytime you change a chemical, just be aware that that could be a problem. Malfunctioning equipment, obviously. It's funny because we'll have people submit samples to us. They'll be struggling. They'll come back, or we'll talk to them after when we report the results, and they'll say, oh yeah, this piece of equipment wasn't working. It's like, well, so why did you test, number one, or why didn't you fix it first, or whatever? Because again, when you fail, you're opening a big can of worms. But housekeeping stuff, I've seen clients that just have fungus or something growing downstream of their chlorination system. So they're actually chlorinating up here, and like right at the end of where it dechlorinates, they'll have some fungus growing on equipment or on sidewalls of basins that cause toxicity. Just need to be sprayed off, cleaned up. Crap in the bottom of basins I've seen be a problem. Seasonal changes, obviously when it goes from summer to winter really fast, the organisms aren't acclimated to that, and you could have some problems. Construction, our facility's currently under construction. We're adding some new treatment processes. And you know, when you're in a construction situation, you're bouncing stuff around, right? You're trying to accommodate the contractors to turn stuff on and off and stuff. And they might be using some new chemical or some new paint, and it's dumped it in the wrong spot, the wrong manhole, right? Stuff happens. So when you got construction going, be careful. New personnel, it's funny how you get people and you think you train them, but you know, oops, I turned on this pump and it should have been that pump, and now you have a problem. I recommend that you always review laboratory data for indications of problems or changes. Laboratory people, if they've been doing it for a while, they have a pretty good sense of what the data should be, and when abnormalities happen, you should be communicating with operations and pretreatment so you can solve it. But then the last of all, ask the wet testing lab what they think the problem is. There's certain kinds of toxicity that have a certain pattern of death or mortality that might happen, so they might have an idea already. Metals are very unique in how they exhibit toxicity, and the labs will know what that is, and they can kind of help you identify that fairly quickly, because the quicker you can identify what the chemical is, then you can start to track back to where is it coming from, and you hopefully can catch them and save yourself a lot of heartache and money, because if it goes to the next step, the TIE, it gets pretty expensive pretty fast. So if you've gone through a plant review, you haven't identified anything or any problems, you're kind of scratching your head. The next thing is to go to a toxicity identification evaluation. The EPA put together a procedure to go through to try to identify what the toxicant is. It's a 3-step process. The first step involves doing a lot of testing. So you take one big sample, it might be 20 gallons, and you do 16 tests on it at the same time. It has different chemical and physical manipulations in those 16 tests to try to identify what it is. Is it an organic? Is it a metal? Is it ammonia? Is it an oxidizer? So you can imagine the cost to do 16 tests all at one time. If that's 16 chronic tests, it's going to be at least $15,000. So you can see it's kind of adding up fast. That's if you can find it with one round of testing. So if you have to do 2, okay, you can see the money thing starting to happen. The tests you do, this is a quick outline of the basic ones that we do at our lab. So you take the sample and you aerate it for an hour. So you do extra air. That's really good to identify surfactants, which are soaps. If your sample's really foamy, right? You aerate it in a graduated cylinder so that it's a column, and it'll actually bubble, right? When you aerate it bubbles up. The soap will stick on the glass, so it actually can take it out of solution, so you can reduce toxicity in that way. The next one we do is a filtration test. You just put it through a normal TSS filter. Is the toxicity associated with solids? Okay. C18 column, C18 is an absorbent of organic compounds. So you pump the sample through a C18 column, takes out any organic compounds. If that is what removes toxicity, then you have an idea that it's an organic. We do a graduated pH test, which you just look as toxicity associated with pH. Does it get more toxic as it at a lower pH or a higher pH? That can tell you, give you information on what the compound is. Sorry. Oh, you're awake back there, Spence? But for example, if you know it's metals toxicity, but you don't know what metal it is, this graduated pH, lead and cadmium are more toxic at lower pHs, where zinc and nickel are more toxic at higher pHs. So it kind of can give you an idea, again, this process is to identify what the toxicant is. So this kind of gives you some hints. The next one is EDTA. EDTA binds up metals and can take it out of solution. So it's a big organic compound that metals can stick to, basically. So it takes them out of solution. So we use that to identify metals. Thiosulfate is a base. What's the right word for it? We use it to dechlorinate samples. So if it's chlorine or another oxidizer, thiosulfate will neutralize it and remove toxicity. And we've also added in at our lab, which is not, so this isn't common between other labs, is we've had a few situations where it's a biological toxicant. Again, something that might be inside the plant that is can cause the organisms to fail the test. So we actually do a UV treated sample. So you take like a liter and you ultra UV it and then test that water. We do a chlorinated test. You know, a lot of plants are going away from chlorine. That seems to be the environmental friendly thing, is to not use chlorine. Chlorine is actually really good. It kills a lot of stuff and actually breaks down a lot of stuff. So now that people are going over to UV, we're seeing some odd toxicity. And so treating it again with chlorine, we just use chlorine bleach, dose it with about 2 milligrams per liter of chlorine for a couple hours, and then dechlorinate it test. That can help, as well as filtration. We've already done a filtered test. That's a normal suspended solids filter, so 1 micron. This filtration is using like a 0.3 micron, so this will take out bacteria. It's basically the filter they used to do coliform analysis with. So it will actually trap the bacteria on the filter. So if it's a bacterial caused problem, that could remove it. So again, we do all these tests at one time. We look at what tests reduce toxicity or increase toxicity, and then we try to figure out what family is it. Is it a metal? Is it an organic? Is it a biological problem? And then you go to the next step, which is, don't have it in there. The next step is actually, if you think it's a metal, you actually figure out which metal it is. And to get that, you just take a sample, take it into the lab, do ICP-MS. That's the lowest detection limit that they have, and look at okay, which one is higher than you think. You use the pH, the graduated pH one is to look for certain ones, and you try to identify which one it is, and then the last step in that 3-step process is you actually, once you think you know what it is, you get some of that in a pure form. So like if it's a metal, you would take laboratory water and spike the metal in and see if you can reproduce the toxicant, the toxicity that you saw at the same concentration. If you can, it's all clean and you're done, right? So let's say it's lead, high lead. Okay, so the lab's identified and confirmed that that's the toxicity. So at that point is where it goes back to pretreatment, right? Because then you have to figure out where's the lead coming from, and then you have to go back upstream and identify the source, and then you have to remove it, right? So metals is usually pretty straightforward. Organics are a little bit tougher. Some of the biological stuff can be tough of where is the real source. Because is it in your plant? Well, or is it coming from somewhere into your plant? So that's a little bit problematic because you can't test influent. So you always have to test effluent. So talked a little bit about cost. It can be pretty straightforward. You don't have to go through the whole TIE process. If you know it's a metal right off, if your lab says it's a metal, you don't have to go through the big process. You can just go down that road, and if you can confirm that that's what it is and identify, go back upstream and identify the source, you can be done pretty quickly. Other things just take a lot of time, and it's frustrating. But some examples of biological toxicants that we've worked with in our lab is Pseudomonas. Pseudomonas is very common in the environment. It's really an interesting thing to identify because the way you do it is you filter it out and onto a media. You put it onto a media, and then you let it grow overnight. You put it in a dark place, shine a UV light on it, and it fluoresces. So it's a pretty cool to see for a lab nerd guy like me. But Pseudomonas can attack an organism, and if you have a cut or something, it can get in there, and that can actually cause abscesses and mortality. Conditions that kind of feed that are low nutrients and warmer temps, and you can have post-dechlorination contamination. So if you chlorinate, if your receiving water is quite a long distance from where you dechlorinate, Pseudomonas can actually grow in that pipe or channel or whatever, and so you treated it, right? It should be sterile or whatever, but you sample at the end of your pipe, right? So you can actually have regrowth or this Pseudomonas just growing on like the sidewalls of the channel, stuff like that. So again, housekeeping is usually important when you have a biological toxicant. We've seen, so with Ceradaphnia are filter feeders, so they eat algae and bacteria out of solution. So Pseudomonas is a potential problem to them. It's not really for fathead minnows. Fathead minnows are more of a fungus and mold problem. And you'll actually see the fungus on the organisms with the fish. It'll be on them. You can see it with your naked eye. It's like white cottony stuff. But again, incomplete disinfection, channels that have, if you've ever, we're in the wastewater business, if you ever see like long, stringy, mossy stuff growing on channels, yeah, if that's downstream of your chlorination and stuff, that's a problem. So we have, this is just some data. Sorry for the people in the back. I'm sure you can't read that. But this is some data on that the standard test that we do, TIE that we do, the 16 tests, and this is the results. And if you can see, we have a baseline test. Okay, that's our control. We're going to compare all of the results of the other 15 tests back to the baseline to see what's different. Okay, so the baseline had an LC50 of 20%. Okay, remember that to pass at 100, so this is actually a really toxic sample. So we aerated it, and we aerated at 2 different pHs. This is the standard pH that the sample came in. We lowered the pH, we raised the pH. Again, didn't really change much. It actually got more toxic at a higher pH. Filtered, same kind of thing. We filtered it at the different pHs. Didn't really change anything. C18, might have taken out some toxicity there. That's a 30 instead of a 20. Okay, pH of 11, it didn't do anything. This is testing the C18 material, where you use a solvent to take the toxicity out of the C18 if it's present. No change there. We did the graduated pH test. At pH of 6, the toxicity is greater than 100%. So that's our first bit of good information. The rest was just, we don't know what's happening. At pH 7, it was 45. pH 8, it's still at 20. So we can assume that the pH of the sample is probably close to pH of 8. Okay. Then we go down and we did the EDTA test with 3 milligrams per liter of EDTA. It didn't really make a lot of difference. We added in some more EDTA, start to see a difference. Added in more EDTA, took out all the toxicity. So what did we say EDTA takes out? Metals. Okay, so that's what we're thinking, right? So we did the thiosulfate testing, really didn't make any difference. So we're suspecting a metal, right? Got EDTA, we're thinking it's a metal that's more toxic at a lower pH. So again, we think like probably lead or cadmium, copper. Okay, so we would pursue from that point. This is another similar TIE test. So we're just like showing you like how to look at the data to kind of help see what the lab does when they figure out the toxicity. So this is a chronic test this time. So the IC25 was 25%. So it's still pretty toxic. We aerated it, didn't really make any difference. Filtering it made a little bit of difference. C18 didn't really change much. Again, pH of 6 helped. Okay, so same EDTA helped. I think I have one more of these. Let's see. Oh, it's in a different format, so we'll skip to that. So, as I mentioned before, once the lab's done with figuring out what the sample is, then it turns over to pretreatment, right? They're going to come to you and say, okay, it's coming from outside of the plant. You guys go find it. So what are you going to look at? What was that? Metal platers, exactly. For a metal, that's, yeah. I've got an example of that one in here. But first you want to review your significant categoricals. Because, again, you know who they are. You should know, hopefully know all your metal platers. If it's a metal, you'll know kind of who, so you'll know the compound, So now you should look at your SIG and CAT list and see who's got that, right? So metal plater, if it's metal. If it's a surfactant, a soap compound, sorry, then you look at like laundries and stuff like that. You might have a laundry or a manufacturer that makes soaps that might have had a bad batch and put it down the drain, right? So you know the chemical, go look at your SIGs and CATs, see what chemicals they have on hand. Go visit them, see what they're doing, right? If it's a guy that makes soap, see if they've changed one of their suppliers and are using a different kind of surfactant. There's probably about 30 kinds of surfactants that are used commonly, and they vary in toxicity a lot, like by factors of 1,000 or 10,000. The more branched they are, the more toxic they are, just as a rule of thumb. So if you know the name of it, go Google it and see the structure of it. The more branched it is, the more toxic it is. Okay, because then it's not natural. And the organisms have a hard time dealing with things that aren't natural. They won't break down in your plant if they're not naturally occurring. It's difficult to break down. Sometimes when they break down, they actually get more toxic. Even though they have maybe less branches, now they're more toxic. So follow up that way. Again, you're going to know what to look for. And then what I recommend is that you know what you look for. Set your samplers in your, we call them trunk lines, but where you get from the different areas, you have main feeder pipes that come into your plant. Just go put a sampler on each one and see where it's coming from. If you've got 5 and it's coming from this one, you can write that limits, or that reduces your area that you're searching. If you have to, just put samplers, go up that pipe until you get there. Where it branches, you put one in this one and one in that one and see where it is, right? And just work your way back to the source. And I've actually seen that actually happen, and it's a house that some guy's manufacturing arrows at home and doing some funky stuff and just dumping it down the drain because he doesn't know, right? Because they're his arrows, right? So we've actually seen that. Along with your SIGs and CATs, who uses this chemical? How much volume do they discharge to you? If you're getting a metal concentration of 100 parts per billion or 1 milligram per liter, think about how much dilution happened on the way to the plant. You know, we have a 20 mgd plant. To have 1 milligram per liter of zinc in the effluent, you've got to have hundreds coming in, right? Because it's all going to separate out into your biosolids, right? Right? Yeah, I see a couple of people are awake and paying attention, right? So you'd have to have a lot coming in because it's going to be separated out into your biosolids. So to have that much in your effluent, it has to be a lot. And actually, the more there is, the easier it is to find. The less there is, the harder it is to find. But see how much volume they have. We have one particular industry in our service area right now that it's a yogurt producer, and we have had several times when we can just look at the lab data and know that it came from them, just because that's the only place who could give us that much stuff. You know, the oxygen drops, you know, the BODs are really high. That's the only place that could give us that much. This, you know, one place. So they wonder why we always blame them. But other questions to ask your lab, your in-house lab or your contract lab, not the wet testing lab, is have you seen this chemical before? So once a year you do your yes, testing. Have you seen this chemical before at a lower concentration? And if you have, and you know what industry it is, go back there, because some things like selenium, that's typically a brick finishing chemical, right? You see that from brick finishers, brick makers. Go back to who you know has that, and maybe you just are barely detectable usually, but if it's selenium is identified as your toxicant, go to anybody who you've seen have selenium in their testing in the past. Can save you a lot of time. Inspections, again, if you have a bunch of metal platers, it's going to be kind of hard to identify who's the problem, but go do inspections and see what strange things are happening. Again, we talked about sampling the trunk lines and followed up the pipe. When you find the company that's discharging this, you're going to have most likely have an enforcement action to go with that, and probably a new discharge permit. So that's kind of the end of my presentation. I can tell you about examples of TIEs that I've done, but let's get the opportunity to ask questions first. Any questions of wet testing?
If the POTW, and this may be subject to, I'm not sure. If a POTW fails a wet test, do the